Quasars, denizens of the distant past, are thought to be the nuclei of galaxies that have a supermassive black hole in them. And that black hole is devouring gas at a prodigious rate. And as that gas is falling into the gravitational field, it shines. It shines and it releases that radiation before crossing the event horizon. Now, this phase lasts for perhaps a few tens or a few hundreds of millions of years, and then the gas in the immediate vicinity of the black hole gets pretty much used up. You know, there was a lot of gas there as the galaxy was forming, but then that gas gets used up and the quasar gradually fades, becoming a less active galaxy, then a more typical galaxy, and then finally a normal galaxy. So here are some luminous quasars billions of light years away when there was a lot of gas in the vicinity of the supermassive black hole. As that gas got used up, the quasar, the nucleus, diminished in brightness relative to the surrounding disk of stars, and you could then see the galaxy beginning to appear. It wasn't so overwhelmed by the quasar light at this point. And with time, the quasar light dimmed even more, so it became a more regular, a more typical active galaxy with not quite such a bright nucleus as a quasar. And then finally a normal galaxy where the black hole is presumably still there, but there's very little gas and dust being devoured by the black hole, and so that central region isn't shining anymore. Well, some galaxies, probably many in fact, don't have a sufficiently massive black hole to have ever been able to swallow material at such a rate that it's one of the brightest quasars. Many galaxies probably had sort of intermediate mass supermassive black holes that aren't able to devour material so quickly, and so they would have never been quite as powerful as a quasar, but they still might have been a regular active galaxy. So for example, this one here may have never been much brighter than it is right now. We just don't know because we can't see any particular galaxy at more than one time in its past. But some of the active galaxies may have been a lot brighter in the past. They might have been luminous quasars. Other active galaxies might have only simply been somewhat active during the time of their accretion, but not as luminous as quasars. In any case, if this is a phase that most galaxies go through for maybe a percent or a few percent of their lifetime, then the prediction would be that most, at least big galaxies in our universe, locally, should have some evidence for a supermassive black hole in their center. That is, the black hole should still be there, but the galaxy looks normal because it's no longer accreting material from its vicinity. Well, in fact, now there is strong evidence for the existence of gigantic black holes in the centers of many big galaxies. And we will find that the bigger the bulge, the bigger the central sort of spherical region of the galaxy, and also the more tightly it's compressed. So the more mass there is and the more it's compressed into a smaller volume, those are the ones that tend to have the very biggest black holes, okay? So it's the black hole formation process seems to be linked with the formation process of the bulge. And the bigger, more massive, more compressed bulges have bigger, more massive black holes. The suspicion that many galaxies have central black holes that are massive came early on when it was found that the emission lines in some of these active galaxies are very broad. So here's a Seyfert-1 galaxy where the hydrogen beta emission line has these wings extending out to red wavelengths way out here and way over to blue wavelengths down there. Comparing this emission line profile with that in a normal galaxy where the line is very narrow, you see that probably there are atoms of gas moving very, very quickly in the nucleus of this Seyfert galaxy. And one possible cause for such motion would be the tugging of gas by a supermassive black hole. But that evidence is indirect, because after all, stars can explode, producing very rapid motions as well. Here's the spectrum of a type 2 supernova, where the ejection velocities that are measured are between 5 and 10,000 kilometers per second. Well, that's similar to the inferred speeds from those broad emission lines in active galaxies. So, gas moving quickly alone is suggestive of a supermassive black hole, but is certainly not compelling evidence for a supermassive black hole, because Stars and winds and all sorts of things can push gas around in a chaotic way, making it look like there's some sort of a massive object pulling on it, whereas actually there's just supernovae going off or big stellar winds or whatever. On the other hand, if you have stars moving very quickly near a black hole, well, you can't just push stars around very easily. You need a strong gravitational field to pull or push stars. Stars aren't just thrown at thousands of kilometers per second by some nearby supernova. A nearby supernova barely nudges a star next to it. It doesn't make it go careening through a galaxy at thousands of kilometers per second. So if we saw stars moving quickly in the central region of a galaxy, we might infer the presence of a black hole. So here's a schematic of that. Here's a star cluster in the nucleus of a galaxy, and the stars near it are moving around pretty quickly, but not wildly quickly. With the same stars present over here, but with, in addition, a supermassive black hole tugging on those stars, the motions become much more rapid. And so one way of inferring the presence of a supermassive black hole is if you see rapid motions of stars in the central regions of a galaxy. Also, if you find a rapidly rotating organized disk of gas, that too would suggest that it's being pulled by a supermassive black hole, because a disk of gas can't be produced by just ejection of gas from a supernova. You can't get a rotating disk in that way. So organized motion of either gas in disks or especially of stars would be a good indication of a black hole if that motion is very, very quick. And the evidence we've found is that many black holes exist in, well, the evidence we've found is that many galaxies have black holes having a mass of between 1 million and 1 billion or a few billion solar masses, and that's really exciting. So this is, one of the great discoveries of the past decade or so, and it's truly one of the legacies of the Hubble Space Telescope. Of the few dozen galaxies where pretty definitive black holes have been found, Hubble has been responsible for a great majority of them. So it's really a great thing that Hubble has done. Here's an example of one of these organized disks of gas and dust in the central region of a galaxy. If you measure this stuff here, you find that it's rotating very quickly. And here's another example of a disk of material surrounding the central part of a galaxy. And again, it's rotating very quickly. So here, if we zoom in on the central region of a galaxy, we can get an artist's impression of what's going on. We're going down, down into the nuclear regions. And surrounding the nucleus, there's this disk of gas and dust, and it's rotating. And measurements of that rotation can then tell you that there's something very massive, this heart of darkness, pulling on the material. One of the most massive black holes known in galaxies is in M87, shown here, the central galaxy of the Virgo cluster, about 60 million light years away. This galaxy has a disk of gas in its central region. The Hubble picture shows it clearly. And if you take spectra of the gas all around this nucleus, you find that it's orbiting very quickly. On one side of the nucleus, the gas is orbiting toward you at 550 kilometers per second. On the other side, it's orbiting away from you at 550 kilometers per second. And all this is occurring just 60 light years from the center of the galaxy. And if you use Kepler's laws or Newton's laws, you can figure out that the mass of this thing is 3 billion solar masses. Okay, it's really huge. Now you have to make a correction for the inclination of this disk and other factors, but that's the mass you get. So here we have the spectra of pockets of gas on either side of the nucleus, and here's an emission line from gas on this side of the nucleus, and it's redshifted by 550 kilometers per second relative to its normal laboratory wavelength. And on the opposite side of the nucleus, the gas is blue shifted. So on one side, it's receding away from you. On the other side, it's approaching you. And if you measure gas all around this nucleus, you can see that there's ordered rotation of a disk. This is not just some gas being blown out by a bunch of exploding stars. This is ordered rotation, as you would expect around some central point-like mass. Now, this particular galaxy is also active. It has this jet coming out of it, seen here at optical wavelengths. Now, if you go down and take sort of an artist's view of what you would see going down into M87, you're going past, billions of stars, and you go farther down into the nucleus. The light is blinding. And then when you get down very, very far in, you can see this disk of material orbiting very rapidly, orbiting some sort of a dark object. And we think it must be a black hole simply because it's so massive and it has in such a small volume that we don't know what else it could be. And there's even a jet of material emerging. Well, as I mentioned a few lectures ago, the strongest evidence for a supermassive black hole in a galaxy actually comes in the form of the Milky Way galaxy. I mean, we have a lot of evidence for stars moving very quickly in the central part of the Milky Way, suggestive of a black hole. There's the region of the Milky Way's center over here toward the constellation Sagittarius. It's in this square. And for a number of years, many astronomers were measuring the speeds of stars closer and closer and closer into the center there, the center of our galaxy. And Charles Townes was one of the pioneers in this effort. He's a professor of physics at Berkeley. And he and other astronomers found that the orbital speed plotted along the vertical axis here versus the radius gives a curve that looks something like this. The speeds are higher closer in than farther out. And if you fit a curve through these points, you get an inverse square root law. You get that the speed is proportional to 1 over the square root of the distance from the center. And you will recall that this is exactly what we have for the rotation curve of our solar system, where the inner planets orbit with a faster speed than the outer planets, and the mathematical form describing the orbital speeds of all these planets is a 1 over the square root of r form. And this is exactly what we expect when there's one central dominant mass and all the other particles are just little guys responding to that one dominant mass. So that curve suggested to Charles Townes and others already quite long ago that there's a massive black hole in the middle of our galaxy. But in the past decade, with techniques such as adaptive optics and other related techniques, people have been able to take a very close look at the central part of our galaxy. I mean, look at how well the stars are resolved in the central region using this technique of adaptive optics. You can see hundreds of stars in the central region here, many hundreds in the central 10 arc seconds or so. So in the past decade, two groups in particular, one led by Andrea Ghez at UCLA and one by Reinhard Genzel in Germany, although he has also a partial appointment at Berkeley, measured the stars in the central region of our galaxy and saw them zipping around some point marked with a red cross here very, very quickly. I mean, look at those orbits. They're fantastic. This star here goes around in just 15 years, and that star there went zooming past some sort of an invisible point there at a speed of 12,000 kilometers per second. I mean, 12,000 kilometers per second, 45 astronomical units from whatever it is that's pulling on it. That already indicates that you've got something of several million solar masses pulling on it. And when you look at all the stars and their orbits together, the common mass that you get from all these orbits is 3.6 plus or minus 0.2 million solar masses, or the most recent measurements. Now, they change every few years, but I wouldn't be surprised if the final number ended up somewhere between 3 and 4 million solar masses for the central part of our galaxy. So we really think that that must be a black hole because we don't know of anything else it can be. And other suggestions that have been made, wild speculations, sound a lot more like fantasy and fairy tales than black holes do. I mean, black holes are now the conservative conclusion. You might think they sound radical and wild and crazy, but no. Black holes are now the mundane explanation for the very rapid motions of these stars. So black holes are not something wild and crazy anymore out in the Wild West, Additional evidence for the presence of a supermassive black hole in the middle of our galaxy comes from the fact that the middle of our galaxy varies in its brightness like a variable active galaxy. And you can see here, in fact, at infrared wavelengths, this central dot here varying in brightness, whereas the other dots are not varying. Well, that dot corresponds to where that red cross was in the animation. That's the center of our galaxy. That's where the black hole is. So apparently there's an accretion disk around our black hole which glows, and you can see it varying in brightness at infrared wavelengths, and also this has been seen at X-ray wavelengths, and presumably it occurs at other wavelengths as well, but we can't see the nucleus of our galaxy at other wavelengths because there's so much dust along the line of sight that it gets, blocked out. Here's a minor flare in the middle of our galaxy where there was a slight brightening at infrared wavelengths over the course of just an hour, and then it faded over the course of the next hour. So the times here are given in minutes. So it's just varying all the time. And what might be happening if you look down into our galaxy is that there are all these stars in a cluster in the central part of our galaxy, but then in the very center there's an accretion disk, and that accretion disk accretes in a variable way. Sometimes there's more material and sometimes there's less. So you get these flares sometimes when you get a lot of stuff being eaten at the same time. Well, the flaring occurs, as I said, over the time scale of about an hour or so. If you ask yourself, well, what's a 1 hour time scale in terms of how far light can travel? It's about 10 astronomical units. Okay, light takes about 8 minutes to go from the sun to us. So a 1 hour time scale is about 10 astronomical units. Well, 40 astronomical units is about the size of our solar system. Okay, so a couple of hours is roughly the size of planetary orbits. That's the time it takes for light to go. If you then ask yourself, what is the Schwarzschild radius of a 4 million solar mass black hole? Well, it's about 1/10 of an astronomical unit. Okay. And so this variability is occurring on a scale of 10 astronomical units. The Schwarzschild radius is 1/10 of an astronomical unit. So this variability is occurring on a scale of around 100 Schwarzschild radii. Well, that's theoretically what the size of the accretion disk should be. So it's all kind of hanging together. The variability is occurring in the accretion disk on a time scale comparable to what we would have expected for the size of an accretion disk emitting X-rays and infrared radiation. So it all kind of comes together here. So that's the best case for a supermassive black hole. The second best case comes from a galaxy called NGC 4258. It has a tiny little disk of gas in the very central region. And that disk of gas has molecules that are actually masing. Now, a maser is kind of like a laser, but with radio wavelengths, microwave wavelengths. And from these clouds of gas that are producing a very intense beam of microwave light, you can actually measure those clouds' positions and motions very accurately. It's a special technique. And what the astronomers who have studied this galaxy have seen is, again, a 1 over the square root of r relationship for the orbital speed of these clouds of gas versus their distance from the inferred center. So this again suggests that there's one dominant central mass having, in this case, 40 million solar masses pulling on these clouds of gas. And the clouds of gas are so close into the central region that, again, you just don't see what else the thing could be but a black hole. I mean, it's causing motions of 1,100 kilometers per second, something like 4/10 of a light year from the very central region. And that means you've got 40 million solar masses within 0.4 of a light year radius. And we don't know what else this thing could be other than a black hole. The black hole is the conservative explanation right now. Then more recently, very good evidence has come for a black hole in our neighboring galaxy, the Andromeda Galaxy, 2.4 million light years away. Now, we've known for over a decade that it probably has a black hole in it, but recent Hubble Space Telescope measurements have really sealed the case, I think. What the astronomers find is that stars are moving around very quickly, very, very quickly in the central part of the Andromeda Galaxy, suggesting that the mass of the black hole is 140 million solar masses in this case. And what's weird is when you look at the central part of M31, the Andromeda Galaxy, you find what looks like two nuclei. There's one and there's another. But more recently then, it has been found with these observations of higher clarity that the nucleus is off here to the right, the upper right, whereas this other secondary nucleus appears to be just a concentration of stars in an overall ring surrounding the nucleus. So you've got this red population of stars in an oblong ring surrounding the nucleus, but immediately around the nucleus there's this curious ring of youngish blue stars, hot stars. And they appear to have formed only 200 million years ago. So let's zoom in now and take a closer look at them. We're going down into the central part of the Andromeda Galaxy, down into the center. I love these zoomed views. Of course, this is all artist conception, right? This is what we infer from the measurements, but we don't have such detailed pictures, of course. Okay, now we have the picture that was known for a long time of sort of a double nucleus. That has been resolved into a nucleus with a ring around it, a red ring of stars. And then surrounding the nucleus itself, there's this much smaller disk of blue stars, spanning only 1 light year in diameter, whereas the other ring of red stars was more like 10 light years in diameter. And this disk of blue stars is rotating around some hidden massive dark object very, very quickly. And those are the measurements from which we infer the presence of a black hole. It's hard to understand how this disk of blue stars would form. Here's an artist's impression of it. It's very close to the black hole, and we would have thought that tidal forces exerted by the black hole would have prevented the formation of massive stars in the immediate vicinity of the black hole. But this just goes to show that we don't understand everything about the universe, and with every new observation that verifies one hypothesis, new questions are raised, and this continues to make science fun. Science is a fun, dynamic process where we confirm some of our hypotheses, have to reject others, but even when we confirm some, there's always new tidbits thrown our way that teach us something interesting about the universe, or which hold clues to something interesting. I mentioned before that the more massive black holes tend to be in the galaxies with the bigger bulges. So let's take a quick look at that. Here's M87, which is an elliptical galaxy. It doesn't even have a disk, so you could think of the whole thing as a bulge. And its black hole is 3 billion solar masses. Here's the Sombrero galaxy with a smaller bulge than M87, but still a pretty hefty bulge. Its black hole mass is 700 million versus 3 billion solar masses. Going to Andromeda, which is an even smaller bulge, 140 million solar masses. See, smaller and smaller. Going down to this galaxy, which my group studied, it basically hardly has a bulge at all, but it does have a star cluster in the nucleus, and we infer a black hole mass through measurements of the stars and other related measurements in this galaxy of 300,000 solar masses. So the smaller the bulge, the smaller the nuclear region, the smaller the black hole. And here's a galaxy, M33, which is in our local group. It's about 2.6 million light years away, sort of toward the direction of Andromeda. Anyway, it doesn't have a bulge at all. It just has this disk that goes all the way to the center, and there's no known black hole in the center of this galaxy. The upper limit for this galaxy is 1,500 solar masses. So if there is a black hole there, it's a pretty puny one. So as you go down in size for the bulge of the galaxy, the mass of the black hole decreases as well. Conversely, and a little bit more subtly, if you have a given amount of mass in the bulge, but it's spread out more, you also have a less massive black hole. Okay, so the more mass in the bulge, the bigger the black hole. The more that mass is concentrated toward the center, the bigger the black hole as well. And we don't understand why. Okay, here's the correlation. 1 billion solar mass black hole inside of a big, huge bulge. 1 million solar mass black hole inside smaller bulges. No black hole inside non-existent bulges. What does this correlation mean? The bulge of a galaxy may have 100 to 1,000 times as much mass as the central supermassive black hole. The bulge, in a sense, shouldn't care about the formation of the black hole. It shouldn't know anything about the formation of the black hole, yet apparently it does. The formation of black holes and bulges is intimately related, apparently. And you might ask yourself, well, how far down in mass does this correlation extend? Does it go all the way down to globular clusters? Well, here's a massive globular cluster in the Andromeda galaxy, and in fact, some astronomers think that it has a 20,000 solar mass black hole in it. So that would suggest that the most massive globular clusters do have black holes. But that's a controversial deduction because some astronomers think that this giant globular cluster in the Andromeda galaxy is actually a little galaxy of its own that's being eaten by Andromeda. And so the black hole formed in this little galaxy long ago, but that's different from a black hole forming in a globular cluster. You know, it's quantitatively a different picture. So people argue whether that's really a globular cluster or not. Then there's another globular cluster, this time in our own galaxy, M15, and it's thought by some astronomers to have a black hole 1,700 solar masses in mass. But that's quite controversial. If you measure the motion of stars in the central region of this globular cluster, you find that their motions are actually consistent with not just a black hole, but also possibly a cluster of old dead neutron stars in the middle. So we'd like there to be, or some of us would like there to be, a picture like this, a smallish black hole surrounded by stars. But maybe there's just a cluster of neutron stars in there surrounded by more normal stars that are moving around very quickly. So we're not sure how far down in mass this correlation extends. What we do know, though, is that some clusters of stars vary so much at X-ray wavelengths that it's as though there's an accretion disk surrounding a very massive object in the center. And in this case, by very massive, I mean only, say, 500 solar masses. That may not sound very massive compared to the millions and billions I've been talking about. But 500 is very massive compared to stellar mass black holes, which are more like 10 solar masses. And when astronomers looked at these variable X-ray sources, like in M82, they saw some of them varying, like that one used to be bright, then it's faint. This one used to be faint, now it's bright. This one was bright, and then it got even brighter. Most astronomers thought that most of those things are just regular X-ray binary stars having maybe a 5 or a 10 solar mass black hole stealing material from a companion star and flaring up as that material gets captured, okay? But if, in fact, some of these things are 500 solar mass black holes, that's big compared to the typical stellar mass. We don't expect stars to have formed with such masses or to have collapsed because they didn't form in the first place, you know. So here we think that if these really are 500 solar mass black holes, maybe what that means is the central parts of some clusters of stars are so dense that you have this inevitable gravitational collapse forming what we now call intermediate mass black holes. Intermediate between the stellar mass variety of 5 to 10 solar masses and the supermassive variety, a million or a billion, found in galaxies. So here's a galaxy with a whole bunch of these X-ray sources. You can zoom in on it with optical wavelengths and then look at it in the X-rays, and the X-rays show all these red dots. Most of those red dots are regular stellar mass black holes. But here is one ultra-luminous X-ray source, which also varies by a lot. And some people think that there's a 500 solar mass black hole there. So that's kind of cool. Now, if clusters of stars formed sort of these intermediate mass black holes, and then the clusters merged together, they would merge and form a bigger black hole. And so maybe that's how the central black holes of small galaxies formed. And then small galaxies, I told you a few lectures ago, merged to form bigger galaxies. So Andromeda formed out of the merger of a bunch of galaxies, we think, and maybe the Milky Way did as well. And in the future, big galaxies can merge, and their black holes will merge together, forming even bigger black holes. And so here's a galaxy where we think that it looks so chaotic that it's the recent merger of two rather big galaxies. And if both of them had black holes, as we think is the case, here they are at X-ray wavelengths. There are two nuclei, so we think that these two black holes are still separate from each other, from these two galaxies that have recently merged but not quite finished the merging process. Well, when they do finish the merging process, the black holes themselves will merge, and that should give rise to the emission of gravitational waves. So here's an animation of how these black holes might merge during the merging process of the galaxies. So the galaxies are merging, they've pretty much merged. Now the nuclei are starting to merge, but they're still separate. So the galaxy is sort of one galaxy now, but there are these two nuclei still orbiting one another. each surrounded by an accretion disk. But as they get closer and closer together, they emit gravitational waves. And the rate at which they emit waves increases as they get closer and closer together until finally it's just an incredible emission of waves as these things merge together. And you can see the artist's impression of these gravitational waves coming out from these merging black holes. So if that's the case, if supermassive black holes merge, we should be able to detect their radiation using gravitational wave detectors. And I mentioned LIGO some lectures ago, where there are two experiments, one in Washington and one in Louisiana, where there are these 4-kilometer length arms, and physicists are trying to detect small contractions and extensions of those arms as gravitational waves come by. Well, that's great. You know, that might measure certain kinds of black holes, but a 4-kilometer length arm is not very big. What you'd really like is a huge baseline, and here is a planned space gravitational wave observatory known as LISA, the Laser Interferometer Space Antenna, which is being planned for the next decade or two. And it will have these satellites whose positions relative to one another are known and are roughly 5 million kilometers. And a gravitational wave coming past our part of the universe through the region of space occupied by LISA should change the relative lengths of these arms, of the spacing between the satellites. And this may allow us to, in the future, actually measure the coalescence, the merging of supermassive black holes in galactic nuclei.